Okay, I'm back. It's about 11:20. Let me try to wrap it up by 11:30 or so. Or maybe it's 11:35, I don't know. Okay, so now I'm back to the main topic, which is our frequency of arrival estimation problem. And we have seen uh, that this FOA problem can be solved uh, either by computing the power spectral density directly, which is one way to do that would be to take the incoming signal and pass it through this bank of FIR filters. And these individual FIR filters are defined by the complex exponentials. And the frequencies of those complex exponentials is to be 0, 1 over n, 2 over n, all the way up to capital N minus 1 over n. Basically, that collection of filters form the DFT of the incoming signal. We take the magnitude squared of the DFT and we do some averaging. That gives us an estimate of power spectral density. The other way that we have said the same solution can be reached is instead of taking the DFT directly, we would first compute the autocorrelation sequence of the incoming signal, again by averaging over capital N samples. And then we would take Fourier transform of that. Now, in either of these two methods, we said that if the incoming signal frequencies happen to be aligned with a multiple of 1 over n, which are our locations corresponding to the periodicity that gives us periodicity in the discrete time domain, then it is fine. Our performance will be the optimal performance. But when capital N is not very large, and in general case, that cannot be guaranteed. Some signals may not kind of end up right on the top of some small k divided by capital N. And in that case, especially if we have multiple such incoming narrowband signals, we may have real problems on our hand. Can anybody tell me what the issues were?
The one was smearing.
Yeah, smearing.
Uh, then we have to take care of resolution and
Yeah. So a low resolution, and when n is small, resolution is pretty small also. I mean, resolution is pretty bad also. Smearing, which happens because of low resolution. And then there was this other problem of signal leakage into sidebands. And we saw that this type of problems can be solved to some extent by applying some window functions. So for example, if we are doing the autocorrelation sequence route, we won't directly take the Fourier transform of the SES, but we will multiply that SES sequence by a window which looks like a bell-shaped curve. And that would allow us to suppress the side lobes. So if our concern is the signal leakage, and because of that some weak signal not getting detected, that problem will probably get solved, but the issue is that we will lose out on the resolution. Our resolution will become worse. And we will not be able to form a null very close to the main lobe. So now we are going to take a look at two different techniques which are going to try to solve this problem. And the very first technique is going to directly leverage property number 5 that we have seen earlier of this correlation matrices. Does anyone remember what property 5 is? It's okay if you don't, because even if you ask me what was property 3, I will not be able to remember. Anyways, so let us look at it. In this approach of FOA estimation, we would start by calculating matrix RxX. Basically, we would do autocorrelation analysis on the incoming signal. We won't do the DFT based estimation of PSE. So first, we will compute autocorrelation sequence. Using that, we will populate this matrix RxX. Remember, RxX elements are filled up by the estimated autocorrelation sequence. Once we get RxS, we will perform eigenanalysis on top of it. And then remember, there was this first part of this property 5, which said that when I do the eigenanalysis of RxX, where the incoming signal has total of k, capital K simultaneously active transmitters, and uh, the, the length of the incoming samples that I am collecting is capital N, then n minus k eigenvalues will all be equal to the variance of the noise. And so when I do EVD of RxX, I will get n minus k values which are all identical. And so I will be able to know what this value n minus k is. I know n because that is my design parameter. I am calculating the averaging window. K is the term that I don't know how many active transmitters there are. But by looking at how many eigenvalues have the identical value, I will identical value, which is the smallest of all, by the way. That was this property 5a. I will be able to figure out the value of k. Okay, let's put this last bullet. Now, that is the case only if I knew RxX perfectly. If I had perfect estimate of RxX, this will indeed be the case. But because I am estimating RxX, I will have some eigenvalues which are going to be small, some which are going to be high. The small eigenvalues may not have all the same values, but they will be still kind of forming a cluster. And so somehow I will have to do some type of little smarter analysis to figure out what are this capital N minus k eigenvalues which are the smallest, and they are lumped together in the same cluster. So in practical implementations, there may be some difficulty to solve this problem, but in the ideal case, this is straightforward. I'll just directly apply property 5a, and in the first step, I will figure out the total number of active transmitters. Now, to solve the problem of FOA determination, I will apply property 5b. So remember what property 5b was. Does anyone remember that? Property 5b said that uh, there is something called signal subspace and there is something called noise subspace. And in the case when capital K is less than n, uh, the noise subspace is going to be defined by the eigenvectors corresponding to sigma square u. And the signal subspace will be defined by all of the other eigenvectors. And property 5b said that any signal which is in the signal subspace has to be perpendicular. The corresponding vector has to be perpendicular to the noise subspace. Okay, that was property 5b. Now the uh, coordinate axis of this noise subspace, the perpendicular vectors, are the eigenvectors corresponding to sigma square u. And so we collected all of those eigenvectors and formed a matrix capital V using those eigenvectors. So that is this matrix V. It forms the perpendicular directions that define the noise subspace. And remember, 5b says that the signal, the actual incoming signal, which lies in the signal subspace, has to be perpendicular to each of these vectors. That is property 5b. So what then I can do is I can define a product W and F Hermitian V, W and F, where F is the parameter under my control. I will vary that from minus 0.5 to 0.5. And for each value of F, I will compute this scalar. Remember, this kind of goes back to the Rayleigh quotient, but here I'm not going to bring that into significance. Basically, I'm going to calculate this scalar and I'm going to define a pseudo power spectral density. This is not really a power spectral density. I can't take inverse Fourier transform of this and get autocorrelation sequence. But still, I'm going to get something like a power spectral density. And the reason is because this pseudo PSD will have peaks exactly at the location of the frequencies of incoming signal. So this quantity that I'm going to calculate as a function of f, ideally, actually, will look a lot like this here. It will have spikes corresponding to f0, f1 to fk minus 1, and everywhere else, that pseudo spectrum will be low. And then basically, I will just calculate the locations of those spikes. Can anybody tell me why this will have the spikes at the location of the incoming signal frequencies? Why this last bullet here, where I'm pointing the cursor to, why this last bullet has to be true? Anyone? Nemishi, what do you think? Nemishi, are you there? Arushi, yes?
Sir, this will be because of WNF. This,
Arushi, you are not audible.
sir, am I audible now?
Yeah.
Sir, this will be because of WFN Hermitian.
Yeah.
Sir, this graph we had plotted earlier, and in this graph we used to get peaks when F minus Fk has to be 0. So whenever
No, but here
F1
I'm
approach,
not doing that at all. When we did that earlier graph, we were looking at that specific summation, sum of complex exponential samples. and that summation ended up being sink shape.
Yes.
That is why we were getting a peak there. Here I'm not doing any of that. I'm doing WF Hermitian V times WNF, and V is defined like this.
Sir, as f approaches 1, WFN, all the elements will turn out to be 1. Is that right?
No, that is not the answer. The answer is related to what I said earlier, that the signal subspace and the noise subspace are mutually orthogonal. They are perpendicular to each other. Okay, who else? Anudeep, you have any thoughts on this? Ishan? Okay, let me say then. So what is going to happen is, as I keep on varying f from minus 0.5 to positive 0.5, or from 0 to 1, which is the same thing, when I end up at a value of f which is same as the one of the frequencies of the input, because of the fact that this noise subspace is perpendicular to the signal subspace, and now this Wn of f is coming from the signal subspace, because I'm saying that this Wn of f actually corresponds to the one of the frequencies of the input. What is going to happen is that this V times WNF is going to become an all zero vector. Basically, all of this, WF and Hermitian V is going to become an all zero vector, because all of this eigenvectors of the noise subspace are going to be perpendicular to the signal frequency. And so obviously all of the dot products are going to be zeros. Does that make sense? Joel, does it make sense what I just now said? I'm looking at this first part, WF and Hermitian V. And I'm saying that as I scan F from minus 0.5 to 0.5, when I approach the actual value of F, which is present in the incoming signal, let us say that the incoming signal has one transmitter which is transmitting at F value of minus 0.25. When I bring my F from minus 0.5, as I bring it closer, and when actually it becomes exactly equal to 0.25, this product, WF and Hermitian V, is going to become all zeros. I'll be actually getting total of n minus k zeros. This WF and Hermitian will, its dot product with A of n will be 0. WF and Hermitian dot product with A of n minus 1 will also be 0. Basically, I'll get a total of n minus k zeros. The reason is that Wn of f, by definition, is residing in the signal subspace, because that is what the signal subspace is. It's a subspace formed by all the signals which are present in the incoming signal. And that signal subspace is, any vector in that signal subspace is going to be perpendicular to all of these eigenvectors. And so this WF and Hermitian V is going to be an all zero vector. And now if I take an all zero vector and do its dot product with some other vector, obviously I'm going to get a scalar which is 0. And 1 divided by 0 is infinity. And so I'm going to get a big spike at the location of f equal to 0.25. Then as I move away from 0.25, this WFN Hermitian V is not going to be all zeros, and so I won't get infinity. Maybe there is another signal present at f equal to minus 0.12. Then again, as I bring f close to minus 0.12, I will again get infinity, a big spike, and so on. So that is the idea behind this eigenanalysis approach. And this algorithm goes by the name of music algorithm. The paper that defined this music algorithm intentionally probably called it multiple signal classification, music. Okay, so it is already 11:40. I'm going to stop here. There is one more algorithm that we will be looking at when we start again on Monday. But this music algorithm is something that I will give you as a lab assignment. And then probably this will also be part of a project that you will be doing sometime in next 2 weeks or so. Okay. I can see that maybe some of you or maybe most of you are not convinced about what I said over here. But then what I say is go back to this property 5b. I think in lab 2, I have asked you to experiment with property 5b. So when you actually do the experiment in MATLAB on your own, I think you will understand what I'm saying here. Okay. Any questions?